because I think we're supposed to go until close to noon. So I've got a much longer lecture that I'm not going to complete, but I'm just going to give you a bit of a historical perspective that may be useful. Craig Cook is going to spend an evening talking about the nuts and bolts of mass spectrometry and so on. And so that's at the tail end of this part of the lecture, but you'll have this in your lecture notes if you want it. But just to give you a background, and I think Kate Freeman will re-summarize a bit of this. In 1912, J.J. Thomson separated neon from neon-22. And this solved a great problem in chemistry at the time, which was that people thought that they were beginning to put together the periodic table of the elements. And hydrogen was 1, helium was 2, and with a mass of 4. So we're getting the masses of the elements. Helium was 4. Okay, and it's about 4. Helium-3 is only 1 in a million atoms, so you can ignore it. Lithium was mass. Well, lithium actually wasn't well characterized. Carbon we knew was about 12, mass of 12. Oxygen 16. Neon was 20.4. And it made no sense. Why should neon be 20.4? Because you can weigh neon. Argon was 40, but neon was 20.4. So everything was in these integer values by 1900. And what he showed is that neon had 2 isotopes, 2 principal isotopes. There's actually neon-21 as well. He didn't see it because it's not very abundant. But with neon-20 and 24, you could tell from the intensity of the beams that they were in about the right ratio, that if you added the intensity on these photographic plates where he's collecting ion beams, one looked like it was a lot weaker than the other one. And maybe that was how come neon was 20.4, because it was mostly this stuff and about 10% that stuff. And that would explain 20.4. So this was the discovery of multiple isotopes in the same thing. J.J. Aston, not J.J., but forget what his first name is. Anyway, he built what's called a double focusing mass spectrometer to really separate beams widely, and then collected these on photographic plates. And so this was the way in which you could actually begin to see that virtually all the elements had multiple isotopes. Okay? And a lot happened. In World War II, it turned out that isotope separation was critical to the war effort in the US and other ways. People had realized you could make a bomb. And so there's a huge effort on understanding isotope geochemistry. In 1947, 2 really important things happened. And both these people had been involved in World War II in the effort, and both of them were kind of tired of of defense and war-related stuff. A guy named Alfred Neer developed a mass spectrometer that is basically the one that we're using today. Okay? What was important, it had what he called double collectors instead of a single collector, had a gas source, and had a dual inlet. And the dual inlet allowed us to analyze our standard, reference, standard, reference, standard, reference. So we could measure these isotope ratios in both of them extremely accurately. And that was what the double collector was for. Okay, so we could measure these ratios really accurately. And at the same time, Harold Urey calculated that isotope differences in the mineral calcite should be temperature dependent if you could use Neer's mass spectrometer. Okay? And he proposed that you could measure the temperature of Cretaceous seawater. Okay? So this is back in 1947. And this actually resulted from his giving a lecture at ETH in Zurich and he had said, well, calcite is a potential thermometer, and I made all of these calculations, and if we can just measure it. And one of the people in the audience, who was a geologist, said, well, if that's true, you should be able to measure the temperature of seawater. So he said, great, we're going to do seawater. And it just shows that even Nobel Prize winners are interested in dinosaurs, because Cretaceous was when the dinosaurs were running around. Okay, so here we have Alfred Neer. Okay, this is the basis for all the modern mass spectrometers. And here are elements. Okay, now we're using not just double collectors, we're using multiple collectors. The first multiple collectors were built in the 1970s. And now they're kind of a standard piece of equipment, but they've actually made it possible to do many things that were just so simply impossible before. Then this is the paper by Harold Urey in the lecture to the Royal Society, in which he says, okay, here's Neer. These calculations suggest particularly interested geology. Okay? And we should be able to see this, should be 30 per mil. We should have this isotope separation of that. Harold Urey says if we use Neer's mass spectrometer, we can measure that. Okay? So this is a very cool thing. So he collected a bunch of postdocs. These are fossils called belemnites. If you want to see what these look like, you can find them on the 3rd floor of the geology department right outside the chairman's office. In this paper with these group of characters, this is the same Charles McKinney that developed the terminology the year before. And they see, oh, here are these these are seasonal temperature changes. So this is the first measurement of seasonal temperature change in the geological record. They're saying, okay, 20 degrees Celsius down to 17 degrees Celsius, 20 degrees Celsius, 17. And this is in the northern Atlantic, okay, very different than today. So this is the actual first time that this had been done. And basically completely changed the way that we do geology. So Harold Urey actually got the Nobel Prize for the discovery of deuterium. He had some postdocs that worked out the beginnings of the oxygen isotope system. Harman Craig, the beginnings of the carbon isotope system. Jerry Wasserberg figured out potassium-argon geochronology, worked on the origin of life with Stanley Miller, worked on earlier meteorites, and then the glacial history with Cesare Emiliani. So if anybody can kind of match that kind of record, they deserve all kinds of stuff. So there's your challenge. That's the highest bar. If you jump over that bar, we'll all say, oh yeah, we knew him back when he was in IsoCamp. Okay. Now quickly, so from 1955 to 1980, there were actually very minor changes in mass spectrometry. The counting electronics got better. Actually, we got transistors. The first mass spectrometer I had big vacuum tubes, which just was just generated an enormous amount of heat and was terrible on things. We got computer control. We actually had the beginning of automation of calcite. And here's our sample size that we have. Everything was done with offline extractions. Okay? So from 1980 to present, this is John Hayes. Okay? So John Hayes was a chemist, but worked with geologists, and actually wanted to separate organic molecules and analyze their isotope values. Okay? So notice here, 1 micromole, 1 nanomole. Okay? So many orders of magnitude better, smaller sample size. Okay? So this is what really changed mass spectrometer. It's still a Neer type mass spectrometer, still a gas inlet, but it's basically under positive pressure rather than a vacuum. and some other things had to happen. The other main thing is we had to have really high pumping systems. So you hear about turbo pumps. The other problem is we need fast computer processing because we have this gas chromatography separation, and the sample is actually fractionated by the gas chromatography system. Kate Freeman will talk in detail about a whole bunch of these issues, but this is really what made the processing of lots of samples available. Okay. All right. So this is the last the slide that I'm going to talk about, and that is that in about 2000, so almost 20 years ago, people were proposing that you could tune lasers to specific frequencies so that lasers could measure the differences in isotope ratios. And that has again opened up a whole new branch of things. Originally, the first time I saw this, I was really kind of skeptical, saying, well, that kind of precision is not going to be useful. But as time has come on, we've got now precise measurements. One of the projects that Jim Ellringer does is he's got one of these things mounted on top of the metro system, on top of tracks. So every day it measures CO2 and water vapor on exactly the same track every hour of the day from 5 in the morning till midnight, and they make an isotope measurement, every 5 seconds. Actually, it's more often than that. Like every single second, they get isotope ratios. Okay, with concentrations of CO2, the isotope ratio of CO2, and so on. So we can actually see as the city wakes up and as the city goes back to sleep every single day, we can see these things. So that just provides completely new opportunities. In spatial, they'll be talking about how you can measure the isotope values of an integrated air column. Okay, so they can measure the isotope ratios of carbon dioxide from the satellite all the way down to Earth. Okay, and then they can do it as it passes over the whole Earth. So CO2 and its isotope ratio. So there's lots of really, really neat things that have been developed specifically for you guys, because you guys are all starting your careers, and so you might think it was for you guys and say, well, that's, take advantage of the great opportunities. Like I said, when there's these big, pollution events, figure out a way to use it to your advantage and learn something about the system. Likewise, figure out new ways to use these instruments. Okay?